Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. So we're restarting a summer tradition that Nati Lineal started here years ago of expository talks. And this one has also a specific aim to prepare us for Ronen Eldan's talk tomorrow. So anyway, happy to welcome James Lee, who will tell us about discrete Ito processes.
I'll tell you about Ito processes, not discrete Ito processes. Okay, so at a broad level, the talk is about correlated sampling, which is what sort of we might call it in computer science, or path coupling, as one might call it in probability. Basically a way of computing a coupling or describing a coupling between two random variables in some kind of filtered fashion. So you sort of slowly sample both random variables, and you're trying to minimize something. So actually, many times in computer science, one is trying to minimize things like communication between two parties. For instance, in communication complexity or in probabilistically checkable proofs. And as you've all said, okay, so the point is that in the Gaussian setting, actually, this correlated sampling, in some sense, is given by these Ito processes, and there's a whole beautiful theory, the Ito calculus, to analyze them. So I want to talk a bit about this today and how you can use it for some geometric applications, and also to set the stage for what Ronen will talk about tomorrow. But actually, let me motivate what's going on now by starting with telling you what Ronen and I proved. So, okay. Okay, so suppose we have a, and by the way, as you've all said, this is supposed to be elementary, so if you have any questions, please interrupt or ask. Okay, so let's start with the function on the hypercube. Okay, and let's define this, what's sometimes called the Bonamy-Beckner noise operator. Okay, so this is an operator which maps f to, at a point x, to the expectation over this random point of the hypercube x hat, where x hat is described in the following way. X hat I is going to be xi with probability 1 minus epsilon, and it will just be a random plus minus 1 independently with probability epsilon. Okay? So you should think about this, for epsilon bigger than 0, you should think about this as some kind of smoothing operator. You average f over small balls, or you can think about averaging it over short random walks in the hypercube. Okay, so just as a sanity check, let's check. Okay, if we apply no noise, then we just get our original function back. And if we apply maximum possible noise, then T1 of f is just a constant function, which is the expected value of f. Expected value over the uniform measure on the cube. Okay? So one might suspect that when you apply this operator, you tend to take functions that were, you tend to smooth functions out because you're doing some kind of averaging. And in fact, okay, it is the case. So let me remind you about hypercontractivity. And here I will list some people in alphabetical order. So in other words, the listing of their names has no bearing on anything. It's a set. I should probably have a better way to do it. Okay. Okay. Which is the following sort of phenomenon that given such a function f, what do we want to say? Okay. For every epsilon bigger than 0, for every p bigger than 1, there exists a q bigger than p, such that if we, okay, such that the q norm of t epsilon f is at most the p norm of f. Okay, so the point here is q is bigger than p. So when we apply some noise to the function and average, the function gets smoother. What's that? No.
On the right.
No. What do you mean? No. There's no constant. In fact, If you want a constant, then it's only known to be equivalent. Well, it's okay. It's false in general that if a Markov operator satisfies this with a constant, then it satisfies it with constant 1. This constant 1 is called hypercontractive. With the constant, it's called hyperbounded. I think this is the terminology that's used. Anyway, it does hold with constant 1. Okay, for some q bigger than p, but this depends only on epsilon and how big p is. Okay, but the point is that the function gets smoother. We went from having an LP estimate to an LQ estimate, right? And so if you think about what this means, for instance, combinatorially, this encodes actually like small set expansion in the hypercube. It encodes something about the isoperimetric profile of the cube. Okay, and this is a very useful kind of theorem. Yes. Yeah. So the point is, it's here. None of the things depend on f. That's sort of that's the point. So there's epsilon p and q such that for every f this holds. Okay. Okay. So now what we want to do is we want to prove something in this spirit, but here we have some a priori estimate on f. We have an LP estimate. So to tell you this conjecture of Talagrand, we want to actually basically make very minimal assumptions on the function f. Okay. So let's simply so let's make the following assumptions. Assume that f is non-negative and has expectation 1 with respect to the uniform measure. Okay. By the way, notice that this hypercontractivity has nothing to do with it's not about cancellation here. You can replace f by the absolute value of f, and this inequality only gets stronger. So this is about non-negative functions. It's not about somehow magical cancellations in this averaging. Okay, so let's take an arbitrary function and just normalize so it has expectation 1 on the cube. So what can we say about, for instance, the tail behavior of such a function? Not very much. We have only the estimate coming from Markov's inequality, which is that the probability that f is, say, bigger than alpha is most 1 over alpha. Okay. We have Markov's inequality. So what Talagrand conjectured, and I'll write the conjecture now, is that if you apply some smoothing via this noise operator to a function, then actually you get tails that are better than Markov's inequality. Right? So so here's a conjecture made by Talagrand in 1989. I'll start this new trend of putting the prize money in okay, so it's worth $1,000 if you can solve it. So the conjecture is the following. For every amount of noise you might want to apply, there exists a function. You'll see where this function comes up in a second. This function just represents the tail that's better than Markov's inequality, such that, again, for every f, so okay, here the assumption applies to the theorem. So f is normalized to have expectation 1. So for every f, probability that t epsilon f is bigger than alpha is at most phi alpha over alpha, and okay. So this phi represents a beating of, not beating sounds violent, but an improvement over Markov's inequality, right? So for every fixed amount of noise, if we average with that noise, then no matter what function we start with, we improve the tail. Okay. So this is the conjecture. Okay. So one thing you might ask is, what could you expect here? So the optimal thing you could get, it would be something, say, some constant depending on epsilon divided by alpha square root log alpha. So the optimal thing you could get is phi of alpha being 1 over square root log alpha. This is achieved, for instance, if f is just a delta function at a single point. And it corresponds, it corresponds to a delta function in the cube. When you apply some noise, looks kind of like it looks like a half space. So more generally, you can think about this. This is tight for balls in the hypercube. Okay, this bound. Okay, so that's the conjecture. I guess I should. So right now the conjecture is open for the conjecture is for every epsilon, but it's still open to prove for any epsilon. and it's open to prove it even if f is the indicator of a set. Okay? Well, it's the scaled indicator of a set, so it satisfies this bound. All right. So the conjecture is still open. I will say that sort of many people actually here worked on this problem. So Ryan visited here for a month years ago, was working on the problem. Jonas Sherman was an intern who spent his whole summer working on the problem. And also, well, Gil told me that he and Eyal and Jeff also worked on the problem during a visit. Anyway, so you can solve it. You can also sort of, more than $1,000, you minimize the future cost of Microsoft employees working on the problem. Okay, so we're not going to talk about this one today, but what Ronen will prove tomorrow is that the Gaussian version is true. Okay, so let's say, what is the Gaussian version? Okay, so I need some objects. One is some n-dimensional Brownian motion. So one can state the conjecture easily without Brownian motion, but it will be fundamental in what comes next. That's one thing. Okay, and I'll take a function now on Rn, non-negative, and let's assume, okay, that the function is expectation 1. Okay, so the Brownian motion at time 1 just has the distribution of an n-dimensional Gaussian. So just to be clear and at the same time introduce, okay. So gamma n is the n-dimensional Gaussian measure. So we assume that the expected value of f is 1. Okay, and then I also want to introduce this semi-group. So, okay, where you start a Brownian motion at x and you average it, and you average the function f under this Brownian motion. Okay, so with this now I can state okay, let me say it this way. The following theorem: for any t less than 1, okay, and say alpha bigger than 2, it's not so important. We have the probability, okay, we'll come back to this quantity in a second, that this is bigger than alpha, okay, is at most some constant depending on t, okay, divided by alpha log alpha to the 1/6. There's also some log alpha term, but since the 1/6 is not tight, since it should be 1/2, let's not belabor the log alpha term. Okay, this is the theorem Ronen will prove tomorrow. I'm not going to say much more about it, except to notice what's happening here. So, what does this look like when we first take a Brownian motion for time t and then average over sort of a Brownian motion for time 1 minus t, right? The right picture is to think about sort of you have a Brownian motion up to some time t, and then you compute the sort of the average of f. Well, you can think about it as the average of f over sort of a Gaussian with variance 1 minus t, or more geometrically, the average of f where you average over the rest of the Brownian motion. You think about a Brownian motion at time 1, you sample it up to time t, and then you average over the future all the way up to time 1. Right?
So here, BT started at 0.
Yes, BT started at 0. Yeah. Okay. Yeah.
Can you repeat everything you just said? Since you started.
How far back?
No, since you started drawing the picture.
Yeah. So okay. So the point is sort of what is this quantity, right? If we went all the way, if t was equal to 1, if we all go all the way to time 1, then what we're just looking at is f of b of 1. When t equals 1, there's no averaging at all, and we're just looking at this quantity. So it's just f, and this is just f at a random point of Gaussian space. So we can't improve Markov for such a function just because you can just you could choose f to be you could just choose f to be the indicator of a set, and then then the tail will be exactly achieved sort of at the level of the set. But now what we say is we don't go all the way up to time 1. We'll run the Brownian motion up to time t You can think about t as close to 1 if you like. And then we'll average over the rest of time, average over the future.
So why don't you just write that expectation of f of d1 given dt?
If you would like, that's another way you can write it. As Yuval is pointing out, you can also think about this as a Doob martingale, which is yeah. So it's sort of the expectation at time 1 given the path up to time t. Okay. So this is the proper analog of the conjecture in the cube, and in fact one can see this is a special case. If you could prove the conjecture for the discrete cube, we would prove it in Gaussian space. Okay, so let me just to finish talking about this. Let me just say that I should mention that Ball, Bart, Bednors, Oleshevitz, and Wolf in 2010 proved that you can get some bound this is not as good as it looked. It's some bound, but the constant depends on the dimension, and in fact it depends exponentially on the dimension. The whole point of this is that it's a dimension-free phenomenon. So so if one, but actually, even to prove it in the case n equals 1 is an exercise, and n equals 2 is already more than an exercise. But the point is to prove it's something here which is independent of dimension. Okay, so that's all I'm going to say about this. Ronen will prove this tomorrow. But now what I want to talk about is sort of the, so now you could think about the case when f is the indicator of a set. Okay, in this case, scaled by the measure of the set, so it has excitation 1. Okay, so now we have some set sitting out here, and we want to prove something about this set S. Okay, so if you look at what's happening here, to study the set S, we sort of take a Brownian motion for some time, and then average average over the future and see sort of like some piece of S under this process. Okay. Now, the problem with doing this process like this is that this theorem is sort of interesting when the measure of S is very small. So if we just took a Brownian motion and tried to study S via sort of like how this Brownian motion sees S, then most of the time, of course, this Brownian motion will wander away somewhere else off in space and will not see any of S at all. Right? I mean, that's representing the fact that there's this sort of 1 over alpha here, when alpha is going to infinity. Okay? So okay, Brownian motion is nice, but it's not quite appropriate to study the geometry of this set S because it rarely comes close to S if S is small. Okay? So what we would want to do is consider a different process. Let's call it WT, which is Brownian motion conditioned to have law f at time 1. Okay? Or if f is just indicator of a set, it's just Brownian motion conditioned to fall in the set. Right? Then if I condition that I fall in the set, then I sort of I get rid of all of this spurious information coming from Brownian motions to just wander far away from the set. Okay? So we'd like to sort of study this property. So one way that you could form such a process is just sample a point of S according to the Gaussian measure, and then just take a Brownian bridge to this point. Now this is not very useful for studying the geometry of S because we're essentially writing S as a union of points and then doing something for every point, right? So this is not generally a good way to study the geometry of a set. What we'd like to do is have something like a Brownian motion, which sort of like approaches S, but sort of slowly, okay? So that it's so that you see what's happening along the way, okay? So what you should think about is we want to have some sort of local process that approaches S, and in general, the process wants to be like a Brownian motion, except for the fact that it has to hit S at time 1. So the process kind of feels some pain at every step from the fact that it's being pulled towards S. Okay? And it turns out that by studying the amount of pain that this process feels, you can say it says a lot about the geometry of S. So for instance, the pain that you're feeling at time 1 will turn out to be related to the surface area of S, which makes sense because at time 1 you're just about to step into the set. Yeah, so that's going to be today. We'll basically study the geometry of sets, like sort of like by empathizing with the pain of this modified process. Tomorrow, Ronen will do what many bad people have done throughout history, which is once you understand something, then you try to hurt it. So Ronen will be basically tomorrow will be sadistic and see what happens sort of like whenever the process is feeling pain, if you push it a little more, sort of see how it responds. Okay, but today we're just being empathetic. Okay. All right. So this is sort of does the general idea make sense? We would like to have this process that lands in S at time 1, but gets there in some slow way that sort of examines the geometry of S. Right? And if you think about it, sort of, if you have this averaging over the future, then when you do this, you're kind of looking at the geometry of S at many different scales. You see it for a while from far away, and then from medium distance, and then closer. Okay. So this is going to turn out to be important. Okay. So the question is, okay, what does it mean? All right. So now let's consider processes that do exactly what I said. Okay. So let's try to see how we could build this W. So okay. At time 0, it's just going to be at the Brownian motion, it's just time 0. And then let's see how. Okay. And then W is going to change a little bit. Okay. So and I want it to change like a Brownian motion plus some drift applied to this Brownian motion. So this is going to, the process WT is going to be of this form, and I want this drift to be predictable. So at time t, you should know exactly what is the drift you want to apply to the process. Okay, and then we want one more property here, and I'll stop writing here because of it's a little bit low, which is that at time 1 we have the law of the f. So what is this thing at time 1? If we integrate, it's the Brownian motion at time 1 plus just the integral of the drift from 0 to t. And I want this, the last condition should be that this is distributing according to f, or if we have a set, just according to the Gaussian measure on the set S. Right? This is the description of the process. And the point is, I mean, you can come up with many such processes like this, right? Like, I mean, you could just, do nothing, just screw around until very close to time 1, and then just suddenly jump, to a point of the set, okay? But we want to consider but you should think about this VT as some kind of, this is the pain the process is feeling. So you'd like to do this in a way that kind of minimizes the amount of pain that the process feels along the way. Okay, so let's, all right, let's give first of all, okay. I mean, obviously, if the set is very small or f is very far from the Gaussian measure, you will have to feel a substantial amount of pain to get there. Okay, so here's one way you can measure pain in terms of the relative entropy. Okay, so this is the relative entropy. So the relative entropy of f with respect to the Gaussian measure is just, okay, it's just the expectation of f log f. This is the definition of relative entropy. And you should think about, okay, just to make sure that sort of everyone's sign conventions are in the right place. If f is sort of constant, if it's close to 1, then it implies that the relative entropy is small. And if f is, if f is sort of spiky, in the sense that it's very far from the Gaussian measure at some places, then it implies that the relative entropy is large. So this is what you should be thinking about.
Classical distribution people are used to that, so that's really the relativity of the measure f gamma n with respect to gamma n.
Yeah, okay. Yeah, so here I've conflated the, Yuval is saying I've conflated this is really f d gamma n. I've conflated the density with the measure, but actually people do this all the time, so I'm in good company to make this choice. And if you think about it in discrete variables, this is if you were, for instance, on the cube, and this was the uniform measure on the cube, then this is like the entropy deficit of f. When f is uniform, it would have entropy 0 because it has full n bits of entropy, and when it was on a single point, it would have relative entropy n because because it has no entropy. Okay, I mean because the corresponding distribution has no Shannon entropy, right? The point being that Shannon entropy and relative entropy have different signs. So, OK. All right, so now let me tell you a theorem. Various parts of the theorem are due to Follmer and to Joseph Lehec. I will say we learned about it from Joseph's work. OK, so the theorem is the following. If you want to, OK, so the relative entropy of F with respect to the Gaussian measure is exactly the minimum over all drifts satisfying star. OK, so I didn't put a star here, but let's call this star. OK, so we look over all drifts that sort of satisfy the fact that at time 1 we have where we're distributed according to the density F of something beautiful, which is this. OK, so the relative entropy of F with respect to the Gaussian measure is exactly equal to the minimum amount of energy you have to expel in order to push the Brownian motion to have a distribution F at time 1. Right? Does the equation make sense? It's yeah. OK, so this is the equation, and even more than that, there's an explicit form for the optimal VT. Which is, I mean, the optimum is attained. It's unique, but let's say, and the optimizer is VT, which is which has this formula that I'll explain in just a second. This formula is also equal to gradient log. OK. OK. Here's the theorem. OK. So what does it say? It says that at every point in time, what you should do is kind of you should look in the direction in which F is increasing multiplicatively the fastest, but it's not F. It's sort of the average value of F over the future is increasing the fastest. OK. So so in a second, I will tell you about the proof of this theorem. But for OK, so but I've decided. OK, in some sense, yeah, this formula looks a bit strange, or I mean, maybe it doesn't look strange. It might seem like it's kind of the right thing. But I want to stress the fact that this is the most natural, obvious thing to do. OK, so so to do that, let's go back for a second to the discrete cube, and let me just tell you the same process in the discrete cube, and then there you'll say, oh, of course. OK, that sort of motivates this form for VT. All right. So now again we have it's the same setup, sort of all the philosophy is the same. We have a non-negative function, expectation of F equals 1, and we like to sample. You can think about it, we'd like to sample a random variable according to according to the density F, right? So how can you do it? Here's a very simple. OK, so we want to sample. Let's, by analogy, sample W according to F. OK, so how might you do it? Well, OK, you might sample the first bit. So remember, sort of W here. This is a random string in the discrete cube. How might you do it? Well, you would first sample the first bit according to the marginal distribution on the first bit, then sample the second bit according to the marginal distribution on the second bit conditioned on the choice for the first bit, and so on. You would just, OK. OK, so let's just compute the biases you would apply at every step, right? At every step you're flipping some biased coin, right, to decide whether you should set the coordinate to be 1 or to -1. And let's just compute the biases, and you'll see that the biases are exactly the analogs of these values. Okay. So, OK, so let's OK, so let's define. OK, so suppose that we've sampled sort of W1, W2. These are the bits of W of W up to I minus 1. How do we sample the next bit? Okay. So let's define Vi to be the expected value of B. So again, analogously to what we're doing over there, B is uniformly random on the cube. Okay. So now Vi will sample according to a uniformly random bit if the past had been the samples we make, sorry, and also if the, okay. So this is the expected density at a random string if we choose how we've gone so far and set the ith bit equal 1. And I'm going to subtract from this the expected value of f at a random string. If it's exactly the same thing. So this, if this is what we've seen so far, but the ith bit equals minus 1. Okay. And then I'm going to divide this by the average of these two things, which is the expected value if you don't condition on what happens to the ith bit. Okay. Okay. So up to I minus 1, W up to Wi minus 1. Okay. And then we should put half here for the formula I want to write down. Okay. And then how will we sample the ith bit? With the ith bit is going to be 1 with probability 1 plus Vi over 2. Yes. And minus 1 with probability 1 minus Vi over 2. Okay. And what we're doing here is just, if we average over the future, we just see this thing, right? So this thing is exactly half of this plus half of this, because this thing chooses the ith bit to be 1 or minus 1 uniformly at random. And so what this Vi is computing is just how much more density is there in the direction of I equals 1 versus in the direction of I equals minus 1. Okay? So it's exactly the conditional probability. This is exactly the conditional probability that it's exactly the marginal probability that the ith bit is 1 conditioned on the choices we've made so far. Okay. And I just want to sort of now, if we define sort of this partial derivative operator, so the partial derivative of G at a point x is, well, set the ith bit to 1, look at the difference when we set the ith bit to 1 versus setting the ith bit to minus 1, divided by 2, then this Vi is exactly the partial derivative of, okay, I'm going to use shorthand. This Fi minus 1 just means that we set, it's just this. This is the divided by this. Okay? So this is sort of, okay, it's just the partial derivative. So you see the formula is actually exactly the same one as the one we put here. This is exactly the derivative of the, at Wt is where we are now. This P1 minus T is averaging over the future. So it's exactly the derivative. It's exactly measuring sort of how much do we, the sort of the rate that we should change multiplicatively. Okay, sorry. Does it make sense what's going on here? These VIs are exactly partial derivatives, so sort of like by analogy, this shouldn't be surprising anymore. This is sort of just like conditioned on the past. How should I sample in the future? That's all I was trying to say. Yeah.
So the definition you're saying is okay, is 1-to-1, but is a theorem, the statement of theorem also very natural to think of over here?
Okay, so there's a reason that everything becomes. So the answer is yes, you can say the same statement. The problem is that in the continuous setting, in Ito processes, sort of like all the expressions are much nicer. So this is actually something like e to the log of 1 plus blah blah blah. But one doesn't need all the parts of log, just needs, okay, I'll say something about that in a second. You can say the same thing in the discrete setting, it's just that the expression will not look as nice. And in fact, it's sort of by necessity, if these VIs are much bigger, are big, if they're not epsilons, then you will not, you will get a different expression. Here, the sort of since you're feeling the VT instantaneously, okay, things work out much more nicely. Okay, let me just say one more thing about this setup, which is also that I can tell you, okay, I can tell you the value of f at this string w just by examining what happens here. So I'll make the claim, and then, so this is wi vi, okay? So this is my claim on f at w, and the reason is just because, if we happen to choose the sign that goes in the direction of vi, sort of like our sign is in the right direction, then the value of f increases by 1 plus vi. And if we choose it in the wrong direction, the value decreases. So if one thinks about it just for a second, this is exactly the no. This is both sides are random variables here. This is exactly what we want. Yes. Yeah, this is a random variable, this is a random variable. Right? Everything is okay. All right, so okay, so now, yeah, let's go okay. So actually I think let's change the order a bit. Now let me give you a couple of applications of this theorem, and then I'll explain to you the proof. The proof, well, I'll explain to you some part of the proof. Okay, we'll see, after I give you the applications, we'll see how much energy people have for the proof. But the applications encode sort of the interestingness of having this minimum energy coupling between some measure that samples from f and some measure that samples, and Brownian motion. Okay.
Just a question.
Yes.
We were taking only the gradient of the operator. What would be the value of the integral?
So what?
So I just take what is upstairs for Vt, I take the gradient of P1 minus Tf of Wt.
Yeah. So you can say, okay, so I mean, it doesn't make sense anymore. It can now be, I mean, if you look over in this setting to what happens, now you'll get probabilities that are bigger than, that are bigger than 1 or less than minus 1. I mean, what will happen, I don't know, but what does it mean, what will happen?
You'll get some process, but
it's
not clear what it means.
It's not clear, no, it's not clear how to even interpret this process. Well, okay, what do you?
I mean, you'll get some, in this case, it is well defined, but
yeah,
it's not going
it's
to
very,
be related to anything.
Well defined. If you ask me if it's better in some sense, I'm not sure, because I don't actually know what is the, I mean, you will not end up, certainly you will not end up in the law of f at the end if you do that. I have no idea where you'll end up. But you see, I mean, if you're not careful, you could like overshoot the set. I mean, you can, if you're not, yeah, you will not end up in the, I think. Okay. I think, but now I have to think about it. But since we're,
Like you will actually. Okay, maybe it's not.
It's adapted, so you won't exactly overshoot, but you could do some kind of oscillatory thing due to this.
It's not clear what will happen at time 1, right? I guess what you're saying is, as you approach time 1, you're sort of, you are insisting that you hit the set, but now you could be jumping over the set back and forth many times, especially if the set has some crazy boundary and you lose this smoothing effect. Okay, so let's pause on this question for a second. Let me tell you one fact about this optimal VT, which will be important. And if we get to the proof of this theorem, then we'll see the fact that this VT is a martingale. Okay, so so for instance, the expected direction at time 1, when you're at time t, the expected direction you'll be pointing at time 1 is the direction you're pointing now. Okay, so all right. Okay, let me give some applications and then then we can talk about the proof. Okay, so the first application is the log-Sobolev inequality in Gaussian space. And I should say also both these applications are due to, are due to Lehec, not the conclusions which are classical, but the use of this to prove them. Okay, so the first thing is the log-Sobolev inequality, which is equivalent, by the way, to the, in the discrete cube, for instance, the log-Sobolev inequality is equivalent to the hypercontractive inequality. So you should think about this as a proxy for the thing we discussed at the beginning. Okay, so for this inequality, we need one quantity of a function, which is its Fisher information. So this is this with respect to the Gaussian measure. And then if you sort of, okay, let me write it also in this way. Which is also equal to this, okay? So if you think about f, for instance, as the indicator of a set, it's just 0 or 1 valued, and then this is really, this is measuring the surface area of the set in some, the Gaussian surface area of the set, at least in some analytic sense, okay? So, okay, so that's the definition of Fisher information. And then the log-Sobolev inequality is just the following. The relative entropy of f with respect to the Gaussian measure is at most 1/2 the Fisher information of f. Okay, so it tells you that if the function f is not, okay, this is most for a set. If the surface area of a set is not too big, then the set has to be then the set has to be fairly flat. Okay, in general, it relates sort of the global ability of f to be different from the Gaussian measure to just sort of to some local property of f. Okay, so let's now, using this theorem, let's just prove the log-Sobolev inequality, and it's really like completely effortless. So okay, so the relative entropy is exactly half. Now VT is going to be the optimizer, half the integral 0 to 1 of this thing. Now we use the fact that VT is a martingale. Expected value of VT squared is at most expected value of V1 squared, right? So this is at most half expected value of V1 squared. Now, but just notice what is V1. V1 is exactly the gradient of f. V1 is exactly the, okay, actually we'd need to do maybe one more. Gradient log squared, this is at time 1. I see. Okay. There was one mistake. There was one problem with going out of order. Let me see how to correct this problem with going out of order. Crap. Okay. What is it? If we look, it's gradient f at w1 square divided by f of w1 square. This is not what we want. We want gradient of f at, let's put expectation here so it makes more sense. We want the gradient of f at sort of a random Gaussian point, not at a point of w1, which is distributed according to f. Okay. Yeah, this is a bit is a bit sad because now I'm going to have to write something, and then okay. So here is the last step of the proof, which you won't be able to understand for a second, and then in the last 3 minutes that I have, I'll explain to you the proof. But this is because 1 over f of w1 is exactly the change of measure that sort of transforms w into Brownian motion. Actually, the whole process wt into Brownian motion. Unfortunately, you didn't see this yet, which is a bit sad because what's that?
W1 is distributed like
good,
f
good,
times
good.
Gaussian, so we don't.
Yeah. Thank you. No, of course. Yeah, you should have said it before I started to do all this.
You already said it. Just recall.
The formula is just, the formula you wrote is right. Just
Yeah.
you don't need explanation.
Okay.
Remember that one of them.
Yeah. Okay, good. We only, okay, this is, here I wrote something stronger, which is that it holds for the whole path. But really, we only wanted at time that at time 1, f, at time 1, this is the change of measure. And the point is that, okay, so, yeah, the point is that W1 is distributed according to f times d gamma. So f of W1 is exactly the, it exactly gives you the scaling of the probabilities, or the scaling of the probabilities, so that you map, that you map W1 to B1. It's exactly the change of measure from W1 to B1, by definition. Okay. That was the proof. Sorry if the beauty was marred by my confusion. Okay. Let me give you one other proof that doesn't even need this change of measure and is a bit simpler. Which is the Talagrand's entropy transport inequality. Okay. So the inequality here is that, so first let me write it. I have to remember what is, here is also a factor of 2. So let's say the inequality is the following. Okay, so here's another inequality, which is that, I'll tell you in a second, the W2 distance from any, again, this is the shorthand for f d gamma n. The W2 distance between any measure and given by a density f, and the Gaussian density squared is bounded by the Fisher, or by the relative entropy. Okay, and just very quickly, what is W2? W2 is it's the earth mover distance between the two distributions. So in general, W2 between two distributions, you can write it as in probabilistic notation like this. So you look at all random variables that are distributed according to mu and nu respectively, then you take a coupling between them. This is on a product space, and you look at the minimum distance here. Equal to the minimum over the best coupling between mu and nu. Okay? You can also just think about it as if you think about them as sort of just like piles of mass. It's the least Euclidean distance you need to move the pieces of mass so that you move the Gaussian mass to f. Okay? So that's W2. So this says that if a function, this is sort of like an information theoretic quantity. If a function is not has small entropy with respect to the Gaussian measure, then actually you can move the Gaussian measure to that function without doing much work. Okay. All right. So now let's do the proof and hope I don't. This should be really easy, so it will be hard to screw this one up. Okay. So this is at most the distance between B1 and W1, simply because this is a particular coupling of the two. This distance is exactly, I erased the formula unfortunately, but it's exactly the, this is exactly the distance when I sample. This is the drift I apply to get from W1 from B1 to W1, right? And now we can just use convexity to say this is at most 0.1 VT square. I guess, strictly speaking, we should put here norm square, which is equal to twice the relative entropy by the theorem, right? So again, you just sort of you give sort of one, again, if you think about the discrete case, the most natural coupling, and then if you just look at the amount you transport over this coupling, it proves this sort of inequality. Okay. All right, so now we're out of time.
7 more minutes.
Okay, so 7 minutes. And by the way, that was your chance to object to the 7 more minutes. You know, I paused. Okay, so now you can ask, okay, how does one prove such a theorem? In order to make the best use of my time, let me just, okay, how does one prove such a theorem? You do exactly, I mean, you just sort of like, well, all right. Let me remind you, since I erased it, what is WT? It looks like, okay, it looks like this. So the point is, this is what's called an Ito process, okay? And there is a calculus for dealing with these things. Just in the end, let me tell you, you know, how. Okay, let me tell you what is the Ito calculus, and it's very simple, but it's somehow very powerful because all of these, you know, it means that basically all the error terms that you wouldn't want to deal with go away in the Gaussian case. Okay, so here is probably the best way to understand the Ito calculus. Consider the function which is e to the bt. Okay, so the exponential of Brownian motion, right? And suppose I want to ask you if this is a martingale. Okay, so I say, you know, basically, okay, is this a martingale? In other words, are the infinitesimal changes of this thing have expectation 0? Okay. Yeah. So if you ever lost 10% in the stock market and then made 10% back and then looked at your bank account, you would know that this is not a martingale. Okay, but here's a proof that it is. Okay, let's just take the derivative with respect to time. So okay, so it's like e to the bt times dbt. Okay, this is sort of how one takes derivatives in calculus, and then just take expectation over both sides. And the point is that okay, this is 0. This is 0 because dbt is independent of bt. It's some, right? So this is equal to 0. Okay, so that so then this thing is a martingale, but of course this proof was BS. And the reason is just, okay, so what do we really want to look at? We're sort of looking at what happens when we're looking at e dbt. So we can expand this by a Taylor series. What do we get? 1 plus dbt plus half dbt square. You guys tell me when I can stop. Okay. Okay, good. We get something like this. And now if we take expectation of both sides, what happens? We get a 1, which is what we expected. We were, you know, if this thing was a martingale, then this would have been 1. We would have just multiplied by 1 in expectation, plus 0. Great. Okay. Okay. The problem is that the expectation of this thing, really, you know, you should think about it as we compute expectation. This is like half dt, if we compute expectations. Yeah, because Brownian motion has, okay, what's that's, you know, sort of non-trivial quadratic variation. Okay, I mean, I just some people believe this immediately, and I don't know if other people are concerned by this.
If the increments are less than order square root of dt, then because of the independence, the cancellations will just make the Brownian motion constant. So you think about
the way you construct Brownian motion is exactly, you know, basically by adding plus minus root dt. This is how you construct Brownian motion from simple random walk. You have a better explanation, Yuval? It doesn't require.
This is just expectation of bt squared is t. I mean,
Okay. So the point is that when you try to do calculus with respect to Brownian motion, the terms that would naturally go away, the second order terms, are actually real things. Okay. So, but everything else goes away. Okay. So that was the whole Ito. That's the Ito calculus. That you know, the Ito calculus is really that like when you do calculus, you know dt squared equals 0, and sort of, okay. I mean, you should think about dt squared is equal to 0. you should think about bt squared as dt, and then everything else, dt times dbt equals 0, and dbt cubed equals 0. OK, you have to worry about the second order term for Brownian motion. That's what the Ito calculus says. So let me just tell you, for instance, the Ito lemma, which is that if I want to compute the derivative, say, of a function of Brownian motion, and also of time, because then normally what I would do here is I would compute the derivative of f with respect to time, and then also the derivative of x with respect to the first variable, dbt. But then Ito says we have to go one more step and compute half delta x square f dt. Okay, so this is the, that's like the whole of Ito calculus. That sort of, to compute derivatives with respect to Brownian motion, you have to include a second order derivative for the quadratic variation of the Brownian motion. OK, so as an exercise, then you can see exactly exactly what your martingale should be, right? So if you look at dbt minus t over 2 and take the derivative, OK, let's just compute what it should be. This is derivative with respect to time, so it's minus 1/2 this, OK, plus dbt plus the second half the second derivative with respect to the first variable, which is just the same thing, dt. OK, good. So you see what happens here, which is that this thing is the martingale term. This thing has expectation 0, and these go away. OK, so this is this is a legitimate martingale. OK, and now that I'm out of time, let me just say that by using this, you can prove the theorem. I can explain it to anyone offline if you want, but this is really all you need, and then you can then you can prove the theorem. So OK, so I guess I should wrap up by saying that Ronen and I know how to, for instance, take these proofs and translate them to discrete cube. So you can use exactly this method of proof to prove the log-Sobolev inequality in the discrete cube. With a little more work, you can use exactly this method of proof to prove log-Sobolev in the symmetric group. It's unclear how much further you can go. But it seems like a very powerful kind of method to do this correlated sampling and then consider functional inequalities along the path of the sampling. I should say it's not a new method, although, I mean, Borel was doing these things for at least 20 years, and many other people. OK, but I mean, this is so clean that it should have a number of other applications, and the theory goes, goes directly to the discrete case via the sort of sampling I talked about. OK, so let me stop there.
Comments or questions?
Yeah.
I think I should have asked you much earlier, but why is it trivial to see that if I use this VT, I actually get F?
Is it trivial to see?
That it is actually one of those things that satisfies your stars, which are no longer there.
I mean, if I have to think about it, it was not trivial, so that's sort of an easy question. But right.
You remember, in the discrete case, we actually saw this is basically the condition.
So Mohit, if you remember.
The limit theorem, you get this. I mean, you can just do discrete and just think about Brownian motion as many discrete increments, and you'll get exactly.
It's perhaps another way to see it is that if you remember before, we wrote down exactly what is f of w. It was exactly product I equals 1 to n 1 plus wi vi, where the vi's were the partial derivatives. So if you write down the same formula over there, okay, then you will see that at time 1 you're distributed according to f. The benefit over there is that when you write down this formula, because of Ito calculus, you only have to, right, this is, if you think, you write this as expectation of log, and then you only have to use the first 2 terms of log, and sort of everything becomes much nicer. But if you just write down the analog here, then yeah, you'll see that that you distributed according to f at time 1. Or what Ronen said, you could discretely approximate all the jumps and then believe it and then transport it here. Yeah.
It's a much better hand-waving argument. Maybe it's not a better argument.
Yeah. That's why I did the discrete case. Because
how long does the continuous proof of this take? If you were to do it now?
It doesn't take very long, but okay, we should do it offline. If anybody's interested, we can stop and we can do the proof. The only issue is that, one thing I don't want to calculate derivatives in front of people because it would be mind-numbing. So, I would have to hand wave over one of the derivatives. You do have to use some Ito calculus somewhere to prove it.
Just following up on this question, if you're anyway going to a discrete world, like in some sense, is there a very natural way to think of it in a discrete world, what this theorem is?
So
this equality.
This here. Like what you're optimizing in a discrete world.
Yeah.
Unfortunately, you can write down a quantity, but it's not nearly as natural. Somehow that's the benefit of going to of being in the continuous case. That sort of like, there are certain things that are much cleaner here. In the discrete world, it's not okay. The discrete world is tough because here you notice to do this sampling, there's no additional randomness. This thing is deterministic. In the discrete world, this was just a bias, and then I had to use some additional randomness to choose the bits. This makes things much uglier somehow. You could.
Some strong duality. Is that what you're writing? Or is that what you're writing? Something like in some converse dualities. Like I agree, you're saying the second term will be some complicated function of VT.
There is some. Well, okay. It's hard to say when duality is not happening because I saw so many times it was happening. But okay, but I don't know off the top of my head. There is a duality here because there is the duality just in the notion of relative entropy. But okay, but I don't see in the discrete case how it would tell you the answer immediately.
Okay, so we'll continue this offline. So thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.